All right, how's it going, party people? Today we're going to be applying the concept of local binary patterns to a k-nearest neighbor classifier. This video is strictly about using Python to implement those concepts. We also go over grayscale, histograms, that sort of thing. This video will not explain any of those concepts, so feel free to use YouTube to view the theory for all that. This video is just for people who already understood those concepts and want to apply it in Python. So as always with any Python project, the first thing you're going to do is ensure you have the correct packages installed. The packages we need to use for today: numpy, skimage, and sklearn. We're also going to be using OS, but OS honestly is a default package and should already be on your installation. Then another prerequisite step for this lab: you're going to want to have a subfolder with the images that you're going to work with. I guess ignore everything here and just pay attention to this. I have a folder in here that contains all the images, and when you step into this, each subfolder contains images of that particular class. So again, this is an object recognition task. So the difference is here we're trying to detect the difference between SpongeBob, like literally a picture of SpongeBob, and a picture of a natural sponge in the ocean, an actual sponge. All right. I'm not going to step into these folders due to copyright concerns, but these are images that I basically pulled off Google that will be sufficient for your purposes here. So we'll start at the top of this code that will automatically calculate the grayscale histogram of a bunch of images that I've collected. First thing, we're going to import OS for localization and for folder stuff so that we can traverse folders. Of course, we're going to be using numpy as our underlying object data type for storing the feature vector. Then we're going to use a lot of skimage stuff, particularly here skimage's IO function to load the images, as well as a function image underscore as ubyte to enforce that the images should be treated as a 8-bit integer after loading. We will use the re-encoder for the machine learning step. This thing basically just takes the labels that we've already given and encodes them with a unique number. That's probably overkill, but you just want to be safe there to ensure that the labels are what sklearn wants to use. All right. These last two things are our machine learning stuff. So we're going to use sklearn's built-in model selection system to automatically procedurally split the training and into training and testing folds. We're then going to use the sklearn neighbors package to bring in our k-nearest neighbors classifier. Now, the reason I'm going to use sklearn's k-nearest neighbor here, or k-nearest neighbor, is that it seems to work better with very low samples. So if you noticed the number of, the number of images that I'm using here, only about 20 images per category, and your neural networks are going to perform very poorly in that scenario. Now, if you wanted to go above and beyond and get like a real image data set, you're definitely going to want to abandon k-nearest neighbor at that point. But for small like toy examples like this, you're going to find that you'll get better results with k-nearest neighbor. And then finally, we're going to use sklearn's metrics classification report. Let's avoid manually calculating the recall and precision here. This classification report will tell you the precision and recall automatically, given the performance of your predictions against the test set. Scrolling down here, what we have is our function to compute the histogram of some sort of image. So the idea is that this function will be given a grayscale image, which is defined by the parameter bins equal to 256, setting the default to be 256, again, because we're going to be using uint 8 images. And here we use np's histogram function on image.ravel, and .ravel will flatten the image so that np histogram will just calculate the histogram off of the pure values in the image rather than having to worry about it being a 2D array. We set the number of bins equal to the input argument bins 256, and then the histogram is all we care about. And notice here that we're returning hist underscore np.sum. So this will normalize, this here will normalize our histogram so that images of different sizes are treated essentially the same. So we're going to make this like a scale invariant process. Moving on, we have some code here. So this is the number of samples in my data set. So 40 again, because we have 20 images and that's per category. We have 2 categories. So 2 times 20 is 40. The length of our feature, 256. So basically, if it's a unsigned integer 8 image, that's 2 to the 8. That is 256, 256 possible tones for the image. And then for our machine learning step, the parameter we have is the percent of data that's used for testing. I realize that it says train percent here. That's kind of like a mislabel. Okay, that's the percent of data that's retained for the testing fold. All right. Moving on here. This is just the folder path for where the images are located, which you saw earlier. We're going to initialize the feature vectors to be empty numpy arrays. Now, this is a slight deviation from what we previously did in class. You create the variable image underscore data, and then you use numpy's empty to initialize an array of the exact size we need. So as far as the feature vector goes, it should be rows, and each row represents a samples feature vector. So the number of rows you have should be equal to the number of samples, which was established as a previous parameter up here. The x-coordinate or length should be the feature itself. So we're using a histogram to describe each sample. That means that each sample has a vector length of 256. Therefore, you're going to want a 40 by 256 vector. And here we're establishing its data type as a double precision floating type. I guess just because it's a small data set, we can probably just use as much memory as we want there. So another consideration here, why am I using np-empties feature? This seems unpythonic because in Python, the underlying list data type has a .append function. Notice here that I'm actually using a numpy array. Numpy does have an append function, but when you append to a numpy array, it actually returns a new array with the entry you're trying to append at the bottom, and it's actually a very costly procedure. So from an optimization standpoint, if you know exactly the number of features and labels that you're using, you're going to want to initialize an empty array of exactly the correct size that you need. All right. Moving on here to the label vector, we're going to initialize a vector, a 1D vector, and that's just the number of samples, right? There's not really a feature length to the label. It's literally going to be a number. We're going to set its data type to be an integer there. All right. So moving on here, I had explained this in a previous class. So what we're going to do here is just sort of redo it, I guess. So what's going to happen is there's a for loop that will iterate through every sample. This variable sample count indicates the point in the feature vector array where we're at. So we will load the feature vector into our feature vector matrix, and then we will march this sort of pointer or index forward by 1 every time we are loading a feature vector. All right. We need to have these separate counters, or rather like iteration points, because here we're counting the number, and you'll notice right away that I'm enumerating over the list of subfolders and also the list of images. So kind of a weird thing going on in Python where we need separate stuff like that. I'm sure that you could actually, if you wanted to, save this as like a list object and then iterate over one by one. I chose not to do that here and to just maintain a separate sample count variable. All right. The funny thing here is that actually the code to just load the images is actually more complicated than it is to run the machine learning algorithm. Whatever. Anyways, let's just run through this and make sure everybody's on the same page here. So the outermost for loop is enumerating over os.listdir folder path. So if you remember what folder path was, this is the folder containing subfolders, and in each of those subfolders in the images folder is our set of images. So the purpose of this is to automatically infer both the number and type of categories, and to procedurally load all the images in each one of those subfolders, assuming that it is of that type. So for example, I have a subfolder named SB for SpongeBob, and all the images in there are images of SpongeBob and should be treated as samples of SpongeBob, all right? So here we're just getting the list of subfolders in our image folder. So it generates, from then on inside this for loop, it generates the subfolders that it should further step into by using OS path join. This is basically a localization step. If you're on a POSIX system, you use slashes in a particular way. If you're on a Windows system, you use slashes in a different way. You'll see this a lot in various programming languages that are basically agnostic to the operating system, like specific scripting languages. And honestly, the purpose of this is just to make sure you got your slashes right, okay? I actually had just a story time, I guess. I did create some software when I was at UCR where I had basically hard-coded the slashes for a Windows environment, and that lab assured me that everybody was using Windows, and then when that software to segment plant cells or whatever it was got to the students there, the one guy that was using it was actually using Mac. All right, so that's just like a something that you learn when making software that might be used by a variety of people that I don't even know if they cover in class really. Localization, I guess. Always use this when you're trying to generate a path. Okay, do not try to append specific forward or backslashes into a string that you're concatenating or assembling. All right, it's a rookie mistake. All right, anyways, so basically this for loop would be iterating over every subfolder. So it would iterate over SpongeBob and then literal sponges. From there, if OS path is there, so a validation step here to just make sure that whatever path was assigned by OS path join is actually a valid path. Moving on in here, now you step into each subcategory and attempt to load the images. So for image file, that's not literally that's just the path basically in OS lister category path. So basically step into the subcategory and get the list of all the images in that subcategory. And then here, if image file, so basically if the name of the image file ends with JPEG, whatever, PNG, BMP, then attempt to load it. Okay, when we attempt to load it, we use io.imread image path as gray true. So this is basically load the image and force it to be a grayscale image with this flag. Previous labs were using a separate function like from the color subpackage in skimage, but it turns out that there's an argument that you can pass to io.imread in skimage to just force it to be read as a grayscale image. And here, this is rather important, otherwise you'll get like warning messages. Once you load it as a grayscale, force it to be an unsigned integer. For some reason, sometimes an image will be loaded, and even though the intensity is between 0 to 255, it may treat it as a floating point. And that's going to cause issues with our local binary patterns later on, okay? So just leave that, basically. So once you've read the image, here's another further validation step. Make sure io.imread returns something. None, by the way, is a special object in Python functions to indicate that nothing was returned. So there might have been an error or something. So basically, if the code failed to read the image, like it was corrupted, basically skip adding it into your thing, all right? Anyways, what we're going to do here is now assume on the assumption that we're finally looking at an image, basically, in our subfolder. We're going to use the compute histogram function that we created earlier up here to, we're going to use the compute histogram function that we calculated earlier to convert the image into its grayscale histogram, 256 bins. So here we are slicing image data. Image data is our big matrix containing all the feature vectors. The y-axis will be the sample count, which is our index that marches forward one by one after each image. All right. Comma colon means all the dimensions basically. So you have a 256 vector that's coming in and is going to be inserted at the specific row and just to take up all the size there. So here the slicing operator will infer the correct size, assuming that the width of that matrix is the same as whatever the function is returning, okay, which happens to be the case. We happen to know it's going to return a 256 histogram, and image data's width is actually 256, which we had set earlier up here, all right? Okay, so let's move along here. Now, and then we march the sample count forward by 1, all right? So all of this basically just to automatically load all the images that you may have placed in your subfolders for whatever classes you have. This code is indeed scalable for multiple classes and obviously for any number of images that you might have in your subfolders. All right. Moving on here, the machine learning step. So here I use the label encoder from scikit's learning package. This might be overkill because we're already kind of encoding it as an integer, but I just wanted to make sure there weren't any issues. We'll just go ahead and alter the labels so they're uniquely enumerated, and then we'll use scikit-learn's test train split to split the data into training and testing folds. Note we're using the encoded labels here, and I did mention, by the way, the percent of test data. For some reason, I call the variable train %. We'll just leave it. And then random state, we'll set it to 1, whatever value you want. So maybe, the last 4 digits of my social security number or something like that as the random state. And then we'll use our k-nearest neighbor classifier. Note that I hard-coded k-nearest neighbor equal to 3. So it will check to see, what the 3 nearest neighbors are and assign the category based on that. KNN fit on our training data, and then predict on our testing data, and then we have a vector of predictions here. Then we'll use the classification report to determine how well we did. All right, let's go and run this thing. All right, so I'm here now in my command prompt. Let's go ahead and run this thing. So Python knn.hist.py. Cool. So we got 92%. Wow, that's a pretty good result, actually. Though I want to point out here, if you're thinking about the difference between SpongeBob and literally a sponge, the color should be very similar, and the texture will be the key here because real-life sponges actually have a very fine-grained texture. So I still expect us to have a much better performance when we shift over to LBP. All right, let's go ahead and take a look at that LBP code now. So this is my LBP code. It's honestly the same thing. The only thing that you're going to do is to create a function that will generate the local binary patterns. So up here, what you're going to do, the first thing you're going to do actually is to import skimage's local binary pattern sub package, and then our function, obviously. So I define this as a function compute LBP histogram for our image. P is the number of neighbors, and R is the radius. So if you just want a simple 8 connected neighbor, where it's just like 1 pixel from the center, leave this as just 8 and 1, basically. Then we call our local binary pattern function from skimage. That should convert the image into an LBP image using the parameters we pass. Uniform, so I might have mentioned this in class, but there were some researchers that determined that for any particular pattern of microtexture, due to symmetry, you can actually reduce it down to a subset of patterns. So I'm not really going to cover that, but we're not going to use that thing that I talked about. We're just going to leave it. So we're going to use the full 256 patterns. It probably would improve your performance if you ultimately did. use the symmetric reduction down to patterns, but it's kind of an advanced topic. So here, it's like the exact same thing as the previous thing. You're going to use histogram basically, but instead of the colors, you're going to flatten the LBP image. Notice that with LBP, you compare the center pixel to every neighbor, and it's a binary notion of whether or not one pixel is greater than the other. So that's like the total combinations would be 2, right? It either is or is not against like 8 potential neighbors. That's 2 to the 8. So that's 256. So we somehow end up with a dimensionality that's exactly the same as the color histogram. So here we will apply our histogram concept to that, and then it'll return LBP hist. And then here we normalize the LBP histogram. Again, very important for when you're dealing with images of varying sizes. I'm actually going to skip all of this because this is exactly the same. All you're going to do is actually change this line so that rather than calculating the color histogram, or I'm sorry, the grayscale histogram, it's going to calculate the LBP histogram. All right. And from then on, you actually don't need to change the code at all, because this code, this machine learning algorithm, is basically taking a feature vector, and it doesn't actually get affected, because here is where you convert the image to its feature, basically. All right, so let's go ahead and run this thing in the console and see what happens. So I got my results up here from the previous step, just so that we can compare them. Let's go ahead and run that LBP code. I'm hoping it does better, but let's see. Whoa. 100%. Wow. That is really good. Well, I did say that I suspected it to be better, right? I guess that makes sense. This is kind of like a toy problem. Can you tell the difference between a cartoon drawn version of SpongeBob versus a real life sponge picture? Yeah, probably. They're really different. And so even this simple machine learning system was able to tell the difference. Where to go from here, some potential directions that you might want to experiment with. Obviously adding more images, adding more categories, that sort of thing. For a proper machine learning problem, you're probably going to want like 100 images. That's not a requirement for the lab. Like if you're watching this video for my class, like 20 is fine, I think. Otherwise, you're going to be spending hours and hours assembling your data set. Other stuff you might want to explore. You might want to modify the code so that a feature vector for an image is actually the color and the LBP histogram. You can totally do that. Let me show you actually what you would want to do if you were going to play around with that. So what you would do is you would go into the file. Note that I said we should just leave the histogram code, right? If you combine both histograms together, each sample is now described by 2 histograms, one for the grayscale histogram and one for the LBP histogram. So that is no longer a 256 feature vector, it's 512, right? Because it's 2 256 length histograms. And the code that you modify is this, where each image data or each row is represented by both the LBP histogram and its histogram. I guess I got that reversed, from when I said it. Looks like I'm doing the LBP first and then the grayscale. You're going to want to adjust the slicing so that only the first 256 elements is the LBP histogram and the next 256 elements are the grayscale histogram. I'm not going to show you the result for this though, partly because I already got 100% with the LBP image, so there's not really going to be an improvement. But I don't know what sort of images you all are using, and potentially you may need both the color and the texture to get a good result. All right, so I'm looking forward to see some interesting results in those lab reports. Hopefully that was helpful. Take care, everybody. Have a great day.